Okay, thank you very much for the introduction. Thanks for the invitation to speak here. I'm very honored to come and speak here at this 25th in a sequence of annual events under one name or another. It's always a pleasure to be in Tokyo. Anyway, so what I want to talk about is not strictly speaking either about hyperbolic geometry or about groups, but it's a subject that has, I think, a lot of very interesting connections to both subjects, to hyperbolic geometry, three-dimensional hyperbolic geometry, and to groups, hyperbolic groups, in fact, certain kinds of questions that turn up in low-dimensional dynamics and topology. And it concerns a class of dynamical systems which are, in a way, close cousins, both of Kleinian groups and the dynamical systems which are Kleinian groups, and the dynamics of rational maps. So it's a natural class of dynamical systems, I think, for the audience here to be sort of interested in. But for one reason or another, it's some subject that's hasn't been in the center of attention. But maybe that's has a potential to change. So what I want to talk about is a very naive sort of question. Some extremely simple, on the face of it, dynamical systems. These are just dynamical systems, semigroups generated by some extremely simple transformations, similarities, Euclidean similarities of the plane, and even contracting similarities of the plane. So the plane here we could think of as the complex numbers, and then a contracting similarity. Well, it has a scale factor, a dilation, which is a non-zero complex number. And if I want it to be contracting, then I want that scale factor to have absolute value less than 1. And then I've specified the similarity if I say the scale factor and also the center of the similarity, the point that's fixed. Well, that piece of information, those two pieces of information, the complex number, which is the center, and the complex number, which is the dilatation, you can package that in a bunch of different ways. Another way of packaging it is in terms of what the transformation does to a typical complex number x. Well, it scales it and then translates it. Scales it by beta and then translates it by alpha. And as I say, I'm interested in similarities with absolute value less than 1. Okay, so you say, well, he can't really be interested in such simple things. Actually, I'll double you. I'm interested in even simpler things. I'm interested in not the arbitrary case of arbitrarily many finite collections of such similarities, but only 2 of them. And I'll further constrain myself by requiring that the 2 transformations have the same dilation factor. So I'm literally just interested in semigroups generated by 2 Euclidean similarities of the plane with the same similarity factor. The only variable is, the only sort of degree of freedom is where are their centers. They're centered at 2 different points. And up to conjugacy, you can take those 2 points and put one of them at 0 and put the other one at 1, say. And then really the only degree of freedom that's left is this single complex number z, the amount that you're dilating. So we're studying a class of very simple dynamical systems, 2 generator semigroups of similarities of the Euclidean plane, parameterized by a single complex number z of absolute value less than 1. All right, so everyone clear what it is we're talking about? All right. And the question, as the questions always are, well, you've got this parameter z, and it parameterizes these dynamical systems. How does the dynamics of this dynamical system depend on this parameter z? All right. So it's natural to try to, if you have a dynamical system, to try to find some sets which are invariant into that dynamical system, and that's somehow where a lot of the interesting dynamics is captured. And it turns out in this case that there's only one really interesting set, invariant set, where the dynamics is interesting, the so-called limit set. And just as you would sort of define a limit set for a Kleinian group as the closure of the set of fixed points of the elements, it's exactly the same here. We've got this collection of contractions, Euclidean similarities of the plane. Each one of them has a center of the similarity has a unique fixed point. You've got this semigroup of elements, countably many elements. All the non-zero elements give you these fixed points. The closure of this set of points, it's some set, it's compact, it's associated in a natural way to the dynamics, and you can sort of draw the pictures that you get here. There's two examples I've drawn here. This is not a single example, but two different examples. There should be a dotted line in the middle, say. So these are two different limit sets at two different parameters, one of them at the parameter minus 0.58 plus 0.33i. It's not a special number, it's just some number. There's the limit set. You can see it looks like, at least there's two big components, a blue one and orange one. Each of the components are sort of, in fact, made up of separate little components, little pieces, so it's almost fitting together like a kind of a jigsaw. Over here, the blue piece and the orange piece are kind of fitting together. The color coding here is just that I had two different transformations, F and G, and when you applied these things in order, if you only remembered the last one that you applied, well, we color the point blue if the last thing that you applied was an F. You color it orange if the last thing you applied was a G, and I guess if the same point is overlapped, then you maybe blue wins. But anyway, so these are just two different possibilities. So I don't know. So there's some kind of complexity implicit in these pictures. Sometimes I think you can just look at these pictures and see a lot of the structure that's sort of going on in there. There's a lot of kind of mathematical content in these pictures. But anyway, there's two, broadly speaking, different kind of phenomena. Yes. Pardon me, what? The semigroup is free. Semigroup is free, yes. Yes. Semigroup is always free. As an abstract semigroup, it's not very interesting. On the left here, the limit set is disconnected, has at least two pieces, and if you counted them at like the level of the pixels, maybe 30 or 40, maybe more, that we can't distinguish. And the guy on the right here, again, at the level of these pixels, appears to be connected. And so this is some basic distinction we can make, and there's different kinds of phenomena that can occur. So this set, lambda, one way to define it is that, well, it's a forward invariant set, and it's the unique, compact, non-empty forward invariant set with this property. And so it's easy to find this set, or at least to define it, to find it as an intersection of sets that you can find more concretely. Pick any set that's big enough to contain this limit set lambda. How do you know that it's big enough to contain the limit set lambda? Well, the limit set lambda is forward invariant, and everything's contracting. So if you have any set D with the property that its images under F and under G are contained inside it, well, then it contains the limit set, because it contains something that's forward invariant, and this is the unique forward invariant guy. Okay? So just pick any big set D, big enough to contain your entire computer screen or something, big enough that all the interesting actions going on somewhere inside that, big enough with the property that F of D and G of D are contained inside it, and then you can find your limit set as sort of an intersection of a nested sequence of sets. Well, if F and D and G of D are both contained in D, then F of D union G of D is contained in D. And similarly, F squared of D, FG of D, GF of D, G squared of D, sort of the four images under words of length 2, they're all contained in D, and they're all contained in the union of D under words of length 1. You can take the union of these guys. You get a sequence of decreasing sequence of nested compact sets. The intersection of all of them is, by construction, forward invariant, compact, and non-empty. So it is, according to what the assertion I've made on this slide, equal to the limit set. So it's easy to find the limit set. Just find some set that's big enough to contain its images, and start hitting it with the words and see what you kind of nest down along. All right. So just take a piece of notation here. G sub n is just the words of length n in the generators F and G. So there's 2 to the n of them. Okay. And so there's this basic dichotomy. I had 2 pictures. I showed you that certain phenomena could occur, and this phenomena turns out to be one of the key distinctions. This limit set, well, either it's path connected or it isn't. In fact, either it's connected or it isn't. It turns out It's connected if and only if it's path connected. It's not so hard to show. And it turns out it's pretty easy to tell when it is connected. It's connected if and only if, well, whatever it is, this limit set lambda, whatever it is, it's made up of f of lambda and g of lambda. It's forward invariant. It's equal to the union of f lambda and g lambda. So it's made of sort of two copies of itself. If those two copies are disjoint, well, they're disjoint, so you've exhibited your thing as a disconnected set. So f lambda had better intersect g of lambda in order for it to be connected, but that turns out to be if and only if. So if f of lambda intersects g of lambda, then you're connected, and then path connected. And conversely, well, one way in which to see that you're going to be disconnected is just to find some set D containing your limit set, or some set D which contains f of D and g of D with the property that f of D and g of D are disjoint. Okay, because D is going to contain lambda, so f of D is going to contain f lambda, g of D is going to contain g lambda. If they're disjoint and compact, then lambda's disconnected. So that's one way to certify it. Turns out if and only if. So these limit sets are disconnected if and only if there's a disk, in fact a topological disk, for which the images under the generators f and g are contained in that disk and disjoint from each other. A closed disk. So such a disk, if you can find it, call it a good disk. It's not going to feature much in this talk. It's only there to certify that the set lambda is disconnected. And by the usual ping-pong argument, you can see that when you have a good disk, the images are disjoint, and the images of images are disjoint further and further. These things are uniformly contracting. You can see at the end you're going to be left with a Cantor set. So if there's a good disk, the limit set is a Cantor set. The semigroup, pardon me, then is said to be a Schottky, and all Schottky semigroups are topologically conjugate, even quasi-conformally conjugate, when restricted to these good disks D. So the dynamics of Schottky semigroups are somehow all the same as each other, and so these disconnected guys, these Cantor set guys, we understand those. Those are sort of reasonably simple or something. Okay. Maybe I shouldn't say ping pong. I mean, you're not in a group here. Maybe it's just the ping lemma or something. So this parameter z parameterizes, so z is a complex number of absolute value less than 1. It's varying in the unit disk. Let's say except for the origin, because we don't want the degenerate case where these things are just constant maps. And you can ask, there's this basic dichotomy, the limit sets are either connected or they're Cantor sets. And so you can ask, well, for which z is the thing connected? For which one is it disconnected? So it's very similar if you're familiar with the situation with Julia sets for rational maps. There's another sort of basic dichotomy there. Say quadratic rational maps, either the Julia sets are connected or they're sort of totally disconnected Cantor sets. And the classical Mandelbrot set just parameterizes the set of Julia sets here, or a set of rational maps, here parameterized, say, by a single complex number, for which the Julia sets are connected. That's the classical Mandelbrot set. So in 1985, I apologize, there's an error in the abstract. I said 88. It's 1985. Barnsley and Harrington studied these dynamical systems, and they defined this parameter set. They called this a Mandelbrot set for pairs of similarities. These are just the set of complex numbers z for which the limit set, lambda, associated to this Schottky semigroup, is connected. So equivalently, the set of parameters z for which this semigroup is not Schottky. So here's a picture of it. I mean, it's in the interior of this thing, which looks like an ellipse on my screen, but looks more round up on the projector. This is the unit circle. There's a dot. 0 is sort of not really in the parameter space. It's missing there. There's some different colors here. It goes black, blue, light blue, but that has to do with an artifact of how hard the program had to work to decide what color to color the pixels. So the pixels are colored if z is in this Mandelbrot set M. So this bluey, blacky thing is this Mandelbrot set M, and this white region in the middle is this Schottky parameter space. Okay. All right, that's fine. These are nice dynamical systems. You might say, okay, these are maybe some younger siblings of Kleinian groups, but maybe they deserve a bit of love and attention too. One reason that I think these dynamical systems are extremely interesting is that they have a very close connection with objects arising naturally in other parts of mathematics, namely roots of polynomials. It's maybe a little bit surprising if you sort of think of them in this way. So if we have, let's suppose we fix some word w in our semigroup, and we ask, so each word w corresponds to some specific contraction of the plane. Which contraction of the plane it corresponds to depends on this parameter z. The word is fixed, abstractly as a word in abstract generators f and g, but as we vary the parameter, complex parameter z, the actual similarity of the plane that w represents is varying. We can ask, how does it depend on z? And the answer is it depends in an extremely simple way. It's expressed basically as a polynomial of degree n, the length of the word, and the coefficients of this polynomial are literally just 1 and minus 1, depending on whether the letters in w are are f or g, together with a wildcard tacked on the end. We have to actually remember what this initial value, the input x was. X only sort of enters into it by popping out at the end by, it's being multiplied by z to the n, and then you get tacked on some polynomial of degree n minus 1, and that polynomial of degree n minus 1 depends just on the word w, not on the input x, and the coefficients just tell you exactly what the generators were making up w. The words, the letters in w, were they f and g. The reason for this is, I mean, sort of somehow this is sort of extremely simple. If we think of our input, if you like, as being expressed as a polynomial in z, what do we do to it? What does f do and what does g do? So f just took x to 1 plus zx, and g just took x to thunder, minus 1 plus zx. You could think of the way these operators are operating now on polynomials in z. What does multiplication by z do to polynomials in z? It's just a shift. Just shifts all the coefficients along by 1 and appends a 1 at the front. We shift the coefficients along by 1 and append a minus 1 at the front. So all we're doing is we're looking at a sequence of coefficients which describe this polynomial transformation, just describe the value of x, and we're just sort of shifting the coefficients along and then appending 1 or minus 1 at the start. So if we apply the letters of w one by one, then we get exactly the coefficients a0, a1 up through an minus 1. Okay? So that's the value. What is lambda z? Well, it's this dynamical set. It's this minimal invariant set. On the other hand, it's the set of values at z of power series with coefficients in minus 1 and 1. Why power series and not polynomials? Well, because this is the limit sets, the things we get by applying elements f and g in some order infinitely many times. Eventually, after we've applied them as many, sort of infinitely many times, what we're left with at the end, this limit set lambda, the point x is sort of receded into the distance. All that's left is a power series whose coefficients record the sequence of f's and g's that you applied in some order, starting with the most recent one at the start. So the values, this limit set itself literally is just recording for you the set of values of power series whose coefficients have a particularly simple kind. And then remember that being in the Mandelbrot set, this was equivalent to saying that this limit set was connected. It's fine, don't need to, yeah. Well, whatever. And this was equivalent to saying that f of lambda intersect g of lambda is non-empty. What's f of lambda? It's the values of power series that with coefficients in 1 and minus 1 that start with 1, a constant term 1. G is the power series that start with minus 1, saying that one of them is equal to the other. Well, you've got, so let's suppose that this is true. So we've got some power series a0 plus a1z plus a2z squared plus ... where a0 is 1, is equal to b0 plus b1z plus b2z squared plus ... where this is equal to minus 1. Take the difference. The difference is, well, something 2 plus, well, whatever it is, a1 minus b1z plus a2 minus b2z squared plus ... And now each of these coefficients is -2, 0, or 2. Right? Because it's a difference of something which is 1 or -1 and something else which is 1 or -1. And if that's equal to 0, well, let's just divide through by 2. And then we've got a power series starting with 1, all of whose coefficients are equal to 1, 0, or -1. And this is 0 exactly, for some such power series, exactly when f of lambda intersects g of lambda, which is exactly when z is in this Mandelbrot set. So that says the Mandelbrot set itself, this Mandelbrot set z, is exactly the set of zeros of power series with coefficients in -1, 0, 1, non-trivial ones. So starting, say, with the coefficient 1, just for non-triviality. And a power series with coefficients -1, 0, and 1, you can truncate it at some point and get a polynomial with coefficients in -1, 0, and 1. And the zeros of the power series can be approximated by zeros of polynomials. And so this Mandelbrot set is, in fact, the closure of the set of roots of polynomials with coefficients in -1, 0, and 1. Okay, so even this extremely simple setup gives rise to quite an interesting set. It's defined dynamically. You can think about its properties in terms of this, the geometry of these interesting limit sets associated to these semigroups of dilations. On the other hand, you may have no interest whatsoever in dynamics and just be interested in polynomials that came to you from somewhere and that happen to have the property that their coefficients are, say, in -1, 0, and 1. You might want to know, if I have a polynomial whose coefficients are in -1, 0, and 1, what do I know about its roots? Well, what you know exactly is that it's contained in this set M. Okay. There's a slight lie here, which is, of course, that anytime you have such a polynomial, you also have sort of its reciprocal. So anytime z is such a root, then also 1 over z is such a root. So really, what I mean here is that this set intersected with the interior of the unit disk is M. But this set is just what you get by taking this set M and reflecting it in the boundary of the unit disk. So there's no information lost in considering the restriction to the unit disk. Okay. So this is a reminder to tell me to move to some multimedia part of the whatever. So, most important of all, there's a program here which implements some things you can do with these semigroups, and it's available from my GitHub page. So this is a program that's been jointly written by myself and Alden. I should have said at the start, I haven't mentioned my work yet, but everything here is joint work with Alden Walker and Sarah Koch. This program, you can download it from my GitHub page and just play with it. I think it's sort of a very interesting, the phenomena that you get, some interesting phenomena that arise here, almost all of which are very easy to see in practice by playing around with examples. It's very easy to formulate some conjectures about these objects, and not so hard to prove them once you've formulated them. The main tool one really needs to get some insight, I think, is to have a practical means of playing with these systems, and so a nice program with a nice interface is something to do. So here on the left, we have a limit set. You probably see, okay, good, the mouse is tracking that. We have a limit set. Here, on the right, we have, well, okay, so it's supposed to be in the unit disk here. It's just black outside. You can't see where the unit disk ends. Here's this parameter space, this Mandelbrot set. This little red dot here is the value of z. Here's the associated limit set. And so in blue is f of lambda. In orange is g of lambda. This red point here, if we zoomed in a little bit, there you go. See, it's not quite, it's in the Schottky space. It's in a white point. Corresponds to the fact that this limit set is disconnected and actually a Cantor set. So this is kind of nice. You can move around and see how these parameters sort of, how these limit sets sort of change as a function of these parameters. When the value of z is real, of course, these limit sets are totally real, and you can get some interesting things there. As you sort of head off into the interior, they can become big and blobby and whatever. There's some intermediate sort of examples where you can sort of get guys with holes, guys that do or don't contain zero, all kinds of interesting kind of phenomena. And then you maybe want to look at some finer structure in this Mandelbrot set, sort of zoom in near the boundary here. Need to sort of increase the resolution a little bit. If you sort of start to zoom in and increase the resolution here, or maybe where do I want to go? There we go. So here's some interesting phenomena that may not have occurred to you if you were a Kleinian groupie, which is these Schottky semigroups. Remember I told you that they're all quasi-conformally conjugate. Their dynamics is uninteresting. Their restrictions to these good disks are all basically the same. It almost goes without saying, we imagine to ourselves, that if they're all the same, then their parameter space must be connected. It can't be that interesting, right? In fact, no. These parameter spaces are disconnected. There are some holes, or at least the computer program tells us. Numerically speaking, there are some holes. Holes correspond to Schottky semigroups. So these limit sets on the left, it looks kind of blocky here, but it's apparently the computer says this is totally disconnected. Actually, it's a Cantor set. It's just a very fat Cantor set. It's hard to distinguish from having some kind of solidity. And it can't be sort of extricated, can't be deformed through a family of Schottky semigroups down into the main component. It's sitting in some weird exotic component. These two sets, these orange set and the blue set, they're not touching each other, but somehow they're linked. They're linked in some kind of geometric way. They can't be pulled apart without, in the process of pulling them apart, having them intersect somehow. It's a little bit subtle because they are, after all, Cantor sets. Topologically, there's no problem moving one through the other by a kind of any motion perturbing it only sort of an arbitrarily small amount in the Hausdorff sense. So topologically, and sort of even in the Hausdorff sense, be easy to move one of these guys through the other. But somehow, as you try to move one through the other, in this world of limit sets, they're forced to intersect. You're forced to find some roots. So it's interesting, actually, to zoom in on one of these guys. And you can kind of see, is it kind of this beautiful geometric picture. They look, these limit sets, I mean, they are Cantor sets, but they look kind of solid. They look like there's a sort of pair of gears here. And the teeth of the gears, the orange teeth here, look like they're locked with the teeth of the blue gears on this side. Switch back to the Mandelbrot set. So there's one hole here that we found. And then if you look at it, now it looks kind of almost apparent that there are other holes nearby. So we can go into one of these nearby holes, a hole sort of orbiting a hole. And the picture looks very similar, except now the teeth are interlocked, and there's a coincidence. If we zoom in on one of these teeth, we see that the teeth themselves have teeth, and there's a kind of linking of these gears at some next level down. So this is very interesting. It's a geometric. It's not really a conformal or a topological phenomena. It's really a geometric phenomena about these sets, is that they have this sort of recursive interlocking structures, these teeth which can kind of get hooked on each other, and they can't be extricated easily, and this is the origin of the holes. Or so, you know, the computer would have us believe. Okay, so that's sort of one thing you can do. Yeah, let's quit that. Another sort of phenomena I want to point out is we go here. There was something that you may have sort of seen or not seen. There we go. In the picture, there's this spike here. There's interesting real spikes here. So these real spikes, it's not hard to show, of course, if we restrict attention to z real. If z is real and of absolute value bigger than a half, then the limit set is connected. And the reason is sort of quite simple. We take, let's say, the interval, and this is some set that's going to contain, so we're going to say z, let's suppose it's real, bigger than 0, let's say real, bigger than 0.5, less than 1, but real. Then this interval, if we say, let's suppose we have our two guys f and g, instead of using this normalization, let me just sort of change the normalization, conjugate, so that the fixed points of f and g are just 0 and 1. Okay, there's two fixed points, I can put them wherever I want by a conjugacy. If I take the interval and shrink it by length z, well, it now has length more than half the interval. So here's f of lambda. I do the same with g. Also has length more than half the interval, they intersect. And the fact that I got the interval as the union of two copies of itself witnesses that the interval is, in fact, the set lambda itself. So we get an entire interval of things connected whenever the absolute value is real is bigger than a half. So this point here, the end of this tip, is in fact a half. And so it's kind of interesting. It's quite prominent. One thing that we sort of led to believe, I think, by our experience looking at you know, things like Bear's slices or Mandelbrot sets or whatever, is that when we look at these parameter spaces, we expect them in some sense to be kind of homogeneous. We don't expect there to be kind of lots of bumps and wiggles and interior points everywhere, but then some isolated spikes. That's a little bit weird. But in fact, this is sort of this phenomena kind of persists. You can zoom in. It's a numerical phenomenon, so you have to these things are very thin, whatever they are, and you can zoom in on them, but they really do persist, and they look as though they're kind of isolated here. We might come back to some examples a little bit later, but let me just, okay. So Barnsley and Harrington sort of studied these semigroups back in '85, and they did some extensive computer experiments. I actually don't know how they did it, because there's some reasonably fast algorithms to draw the pictures that I just drew, especially of M, which they didn't know, these algorithms. And other algorithms, naive algorithms, are much slower. If I just give you a bunch of points and ask you whether it's connected, it's not so sort of easy to tell. And so they were using also quite old hardware. It's not so clear exactly how they drew such detailed pictures. But anyway, they did extensive computer experiments, and they verified this fact that this Mandelbrot set M has these, what I'm calling here, real whiskers, meaning these real spikes that emanate, that sort of spike out into the interior, and at least in some neighborhood of the points plus or minus a half, they really are, the intersection of M with a little open neighborhood of that is totally real. So if you have a zero of a power series with -1, 0, 1 coefficients, which is real and has absolute value pretty close to a half, it can't be approximated by a zero of such a power series which has some non-zero imaginary component. That's an interesting kind of rigidity phenomenon that they discovered. They conjectured a lot of things about M. They studied it extensively and discovered a lot of interesting phenomena which they couldn't prove. One thing that they conjectured was it looked connected to them. So they thought, well, surely M itself is connected. They thought it would be locally connected. These things were proved a few years later by Thierry Bouch in 1988. And Bouch developed some quite useful tools and techniques which, for instance, let you actually explicitly construct paths in the set M. You can't control them exactly, but you can say maybe approximately where they are. You can do something with that. Barnsley and Harrington actually noticed experimentally that there were some of these holes, and they asked explicitly, they asked the question, are there holes in this set M, these exotic components, apart from the big hole in the middle, are there these little holes, these exotic components of Schottky semigroup space? And that was rigorously proved by Bandt in 2002 as a computer-assisted proof. And he proved that basically using these paths, approximate paths, that Bouch showed that you could find in this set M, and part of his proof that the set was connected, path connected. So one thing Bandt couldn't do was he noticed that there were apparently not just one hole, but infinitely many. These holes, they had little holes sort of nearby them, and the little holes had even littler holes sort of around them, satellites, and they looked certainly to Bandt as though there were kind of infinite sequences of little holes, and he would have liked to prove that there were infinitely many of them, and he explicitly asked if there were. But one of the things that obstructed him was that he didn't really have some good tools for finding interior points in M. It looked to him as though M was pretty solid, but occasionally had a few little holes in it. And one thing that he couldn't really manage to prove was that there was, where M appeared to have a lot of interior, it was hard for him to show that there was actually interior. So he explicitly conjectured in 2002 that M should have dense interior away from the real line. The reason you need to exempt the real line is exactly this fact already observed by Barnsley and Harrington, that there are these real whiskers, these spikes that come in along the real axis. They're not in the closure of interior points. So the real line certainly has points where the interior is not dense. But are those the only places? Are those the only whiskers? So this conjecture was studied over the last sort of 10, 12 years by a few people, most prominently by Solomiak and some of his co-authors. Solomiak and Zhu showed that this Mandelbrot set M has dense interior, at least in a neighborhood of the imaginary axis. So as far away from the real axis as possible. Maybe the geometry is a little bit easier to control, and they were able to show this. Also, another observation that Bandt made was that this Mandelbrot set exhibited a lot of interesting apparent self-similarity at certain points. So those of you familiar with the theory of Julia sets and Mandelbrot sets will know that the Mandelbrot set often resembles, at many points on it, the Julia set that it parameterizes. And Julia sets are at least conformally self-similar. So Mandelbrot sets, one knows and expects them to have a kind of self-similarity that they inherit from the dynamical systems that they parameterize. So that was something Bandt observed experimentally, and some way towards proving that. Solomyk proved the self-similarity of M at some points, at certain kind of points that Bandt calls landmark points. So one of the problems, so there's a natural strategy then to try to prove that there are infinitely many holes. Try to find an apparent limit of a sequence of holes at one of these landmark points, and then use the self-similarity to show that numerically there's one hole, and then the image of that hole under these self-similar sets should give you infinitely many holes which converge down to that limit. The problem is exactly that this self-similarity that Solomyk was able to establish, it wasn't sort of, didn't necessarily respect the topological properties of the set. It was self-similarity in the sense of Hausdorff approximation. It says if you took the set and you rescaled it and you compared it with the set unrescaled, then it was Hausdorff close. And in the limit, it got Hausdorff closer and closer and closer. Well, sets with interior can certainly be Hausdorff limits of totally disconnected sets. So that doesn't really say anything at all about the topology of these sets. And exactly what's missing is some control over the interior points in M. So the problem then is exactly to find good tools to find and understand interior points in M. And so that's the remainder of my talk is about this subject. So there's two methods, two key methods, and both of them are important to certify interior points. There's an analytic method. It's discovered by Bush. It's not so hard, but it's a very nice and powerful method using just Hausdorff dimension. And there's a topological method using traps. So I'll talk about what was known first. Okay, so the very first thing that Bush, one of the very first observations Bush made in his paper is that M actually has a huge amount of interior. It contains the entire annulus of complex numbers of norm between 1 over the square root of 2, approximately 0.707, and 1. It contains this big, thick annulus. So there's lots of interior points. And the proof is very simple, actually. It's sort of basically almost sort of a counting argument. There's just not enough room in the plane for a Cantor set, which is self-similar under dilations, where the dilations don't dilate enough. Somehow there's not enough room. You've got two copies of something in the disjoint. Then the copies, if you're made of two copies of yourself, and those copies are disjoint, the copies have to be definitely smaller. Okay, and the reason, so you just think of it in terms of Hausdorff dimension. We think of our set lambda here. Maybe it's a union of two sets, f of lambda and g of lambda. So let's suppose that our guy is Schottky. So let's suppose that lambda really is the disjoint union of f lambda and g lambda. And let's suppose that the Hausdorff dimension is D, okay? So what does it mean to say the Hausdorff dimension is D? Well, the Hausdorff measure of the set is defined for any Hausdorff dimension, but it might be 0 and it might be infinity. And there's sort of some crucial point below which it's always 0, below which it's always infinity, and above which it's always 0. At the threshold value, it might be 0, it might be infinite, it might be finite and non-zero. Let's suppose, for the sake of argument, it makes the argument much easier, let's suppose that in the critical dimension D, that the Hausdorff measure of this set is, D-dimensional Hausdorff measure is positive, but finite, okay? Well, whatever it is, if you take something and you scale it linearly by some factor, the D-dimensional Hausdorff measure scales by that factor to the power of D. That's almost the definition of it. So whatever the Hausdorff, D-dimensional Hausdorff measure of lambda is, well, it's equal to the Hausdorff measure of f lambda plus the Hausdorff measure of g lambda. But this is just, well, scale z to the power of d times the Hausdorff measure of lambda. and so is this. Well, so 2 times z to the d is 1. Okay, so that tells you what d is in terms of the absolute value of z. No contradiction yet, except that this is a subset of the plane, so its Hausdorff dimension, whatever it is less than or equal to the Hausdorff dimension of the plane, which is 2. And just from that, you see that the absolute value of z has to be less than or equal to 1 over the square root of 2. So conversely, if the absolute value of z is bigger than 1 over the square root of 2, you couldn't have been Schottky. So you have to be in the Mandelbrot set. So the Mandelbrot set contains that entire annulus. Okay? So it's just really, I mean, Hausdorff measure, another way of saying it is this is really a counting argument. There's just not enough room in the plane to fit 2 copies of yourself in you unless you make yourself definitely smaller. Okay. So that's sort of that's the analytic argument. So the next argument I want to talk about is a topological argument. It's a little bit more subtle, but we end up being able to prove a bit more with it. And so there's an ingredient that goes into it first that I have to prove, a lemma which has to do with the geometry of lambda. So supposing lambda is in fact disconnected. Well, you can ask, how big a neighborhood of it do you need to take before it becomes connected? Okay, it's a compact set, so you draw a big enough disk around it, you get something connected. What's the smallest neighborhood you need to draw around it to get something connected? Equivalently, what's the smallest number with the property that any 2 points in my set can be joined by a path which sort of hops from point to point, and the hops are bounded in size. Okay, so I want to sort of find, maybe my set lambda is not path connected, but I want to sort of find, paths which are pretty close to being connected, little sort of sequence of dots which are pretty close to each other, a sequence of short hops that I can use these short hops to get from any point to any other point. So the observation, and again, it's a very simple observation, is just the fact that whatever the biggest gap is, it's a gap between f of lambda and g of lambda. Right. Well, so there's the statement of it there. It says that if there's a point in f of lambda which is within distance delta of a point in g lambda, then any 2 points in lambda can be joined by a sequence of points in lambda such that the distance between successive points is at most delta. Okay, that's sort of equivalent statement here. So here's f of lambda, whatever it is, and here's g of lambda, and the distance between them, there's some point between the 2 of them where they come within distance delta of each other. So now I want to get between any 2 points. I want to get between, say, this point here and maybe this point over here. Well, so I want to do it in a sequence of stages. If I can get from this point to this point with small hops, and I can get from this point to this point with small hops, well, then I can get from this point to this point with small hops because I explicitly know that this distance is only delta. But then I say, what is f lambda? It's just a copy of lambda, but scaled. So it just basically looks like 2 pieces of lambda. And now the size of this gap between them, there's some way to get from here to there where the gap between them is the absolute value of z times delta. So now I want to get from here to there. Well, I get to this point here is like the bridge, and I hop over the bridge, and I get to here. So recursively, all I need to know is that eventually I can reduce the problem to getting from anywhere to anywhere else by short hops in one of the images of lambda under a long word. But these semigroup elements contract uniformly. These images of lambda under this long word, eventually the diameter of that set is very small. So obviously you can get from any point to any other point by a short hop. There's just a single hop will get you there. So this is a very simple argument, but it's sort of nice. It tells you that this set, lambda, has a nice neighborhood which is path connected. The size of the neighborhood you have to take is half of the distance from f of lambda to g of lambda. So then you can take that fact and apply a transformation u to it. So pick a word u of length n, take lambda and apply u to it. We get a copy of lambda which has been scaled. It's been scaled by a factor of z to the n. So now the neighborhood of size delta on 2 times z to the n of that is path connected. Okay? So now we want to bootstrap this fact in the following idea. So this is the idea of a trap. So this is a slightly messy slide, but the basic idea is not too complicated. So what's the idea? So the idea is we want to prove that f of lambda and g of lambda intersect. And we want to do it in such a way that that proof is robust, because we want to prove that the point that they intersect is an interior point. So we want to prove that these two sets, f of lambda and g of lambda, intersect, and we want to prove it in such a way that the proof is stable under perturbation. So we want to prove that f of lambda and g of lambda intersect for a topological reason, because it's the topological reason that's going to persist. So the way in which you prove that, say, paths intersect in topological spaces is you use homology and just show that some endpoints, say, separate each other. So the idea is to look for little copies of lambda inside itself. So here's a copy of lambda here, and there's a little red dot here which I've magnified. And this, what I've magnified is, I've got here now two copies of lambda. I've got two words, u and v, of length n, and n here we suppose it's pretty big. So these are two little copies of lambda. They've been rescaled by a factor of some big sort of macroscopic factor, so we can see them there on the board. So there's a yellow one and the blue one. So I've got two copies of this limit set, the images under u and under v, and I take these neighborhoods of them which are guaranteed to be path connected. So this yellow tubular neighborhood is path connected. The blue tubular neighborhood is path connected. And I take these two copies and I ask, I want them to intersect transversely. What does it mean to say they intersect transversely? It means if I take their union, I can sort of find 4 points in the front here in the correct symmetric order, P1, Q1, P2, Q2, which are in the first set but not the second, and the second set but not the first set but not the second set but not the first. So what I know is that any 2 points in the blue set can be joined by a path in the blue set. So I join them by a path in the blue set. Here it is. I know any 2 points in the yellow set can be joined by a path in the yellow set. Here's the path. Maybe it does this, goes back, does something like that. And because of the separation property, the fact that the 4 points link on the front here, just for topological reasons, the yellow path and the blue path intersect. Now, the yellow path and the blue path are not in u of lambda and v of lambda. What they're in is, this one is in the z to the n delta over 2 neighborhood of u of lambda. This is in the z to the n delta over 2 neighborhood of v of lambda. So I don't know that the blue path and the yellow path intersect. I don't know that u of lambda and v of lambda intersect, but I do know that they have points which come within distance z to the n times delta of each other. Okay, so the conclusion of this picture is that the distance from u to lambda, v to the lambda, is less than or equal to z to the n delta. That's what this topological picture tells me has to be true. But then, I mean, I just get I can bootstrap this. The distance from f of lambda to g of lambda is at most delta. So it's probably a factor of 1 that it should be z to the n minus 1 maybe there. So the distance from f to lambda, g to lambda is certainly bounded by the distance from u of lambda to v of lambda, because u of lambda, well, this is a subset of f of lambda, and v of lambda, that's a subset of g of lambda. On the other hand, this was equal to delta, or this was, on the first hand, this was supposed to be equal to delta. And then on the other hand, this is less than or equal to z to the n, whatever this distance was. So it then follows that this distance is 0. Okay? So this is the point. You kind of use an approximate coincidence at some big scale, and then you use topology at this small specific scale where we have the words u and v, topology to show that the approximation at the big scale can be bootstrapped at this smaller scale. And then you've got the holes are smaller than you thought they were, so then they're smaller still than you thought they were, so they're smaller still, and by induction there are no holes at all, and actually these things are forced to topologically intersect. So it's sort of a method of shrinking holes. You use each estimate tells you that the next estimate is better. So the point is that this property of having this trap, that's obviously something which persists. It's something which is it's an open condition in the parameter z. So when you can find a trap, a pair of words u and v, starting with f and g respectively, such that the translates of the limit set appear to cross in this transverse way, then you've certified that your point z is an interior point in M. So this is a topological way of finding interior points. Okay. So this raises a natural question, a geometric question. Sorry, yeah, is there a question, Jeff? Okay. So there's a natural, so what am I looking for here? I've got these two sets, and I want them to intersect in this kind of transverse way, that each guy bulges out of the union in two different ways. So I want each one sort of transversely cross the other. What are these sets? I've drawn one here as this yellow thing, this blue thing over here. They have no apparent resemblance to each other. But actually, these sets, this set here is just the image of lambda under u. This is the image of lambda under v. They both look like a copy of lambda, but rescaled, and they've been rescaled by the same amount. So up to similarity, this just looks like two copies of the same set. One's been translated relative to the other. So here's a basic question. If I just have a closed, connected subset of the plane, let's say it's full. So maybe just topologically a disk. I've got a topological disk in the plane. When can I translate it so that it intersects its translate transversely? So given, here's the question, given x, a complex plane, let me just, for the sake of argument, let's suppose topologically a disk. When is there some lambda such that x and x plus lambda cross transversely? By which I mean that if you take x and x plus lambda, and I realize they don't look like that, that there are 4 points in the front here which are in one set but not in the other, which alternate in the cyclic order between being an x and being an x plus lambda. And the answer, well, it's already up there, so it's probably not so surprising to you if I say it now. It's exactly, you can do this even only if the set X is not convex. And the proof is extremely simple. So if you have a set that's not convex, there's some supporting, here we go, Hahn-Banach theorem. Some supporting hyperplane, which is the intersection's not connected, and then I can just take the set, and I can just translate it, take the top point into the interior here. And now, well, it goes up, and there's something over here. I've got P1 here, I've got P2 here. This extremal point is Q1. And whatever the rightmost point was over here, the rightmost point over here is even further to the right. So that can be the point Q2. And so it's very easy. So that's the construction. So there always is some complex vector lambda that'll do. And so we're not finding traps is not ruled out in principle because of the shape of lambda whenever lambda is not convex. So here's another lemma that you need to prove in order to make use of this observation, which is, well, the sets we want to be transverse to find traps, they're copies of lambda, so they better be non-convex. So you might just want to know, what are the values of z for which this limit set is convex? And it turns out you can just completely answer that question. It's quite constraining. In order for these limit sets to be convex, it's sort of if and only if the argument has to be rational and the absolute value has to be big depending on the denominator. Big enough, close enough to 1 depending on the denominator. So R has to be at least 2 to the minus 1 over Q, where Q is the denominator. Okay. And so you can plot these convex values here in red, overlay them on the set, and you notice by a remarkable coincidence, every single one of these convex parameters happens to be in this lucky annulus that Bush has already proved for you is in the interior. Only just makes it for the points at 2 to the minus a half I and minus I. All these guys are already in the interior, so we don't need to worry about them, exactly except for the real spikes. So the real spikes, these are the guys for which the limit sets are convex. Convex means we can't possibly use this technique of traps to find nearby points in the interior. And just as well, because there are no nearby points in the interior. And those are exactly the ones we needed to avoid. They're exactly all on the real axis. So that means that in order for the sake of proving this conjecture, we need to restrict ourselves. We can restrict ourselves to values of z for which the limit set is non-convex. So now the limit set is non-convex. We know that there's some possible vector lambda such that if we took two copies of our limit set and translated them, they would intersect in the correct way and prove we had a trap. And so there's just a sort of an argument to get something of this kind. So here's sort of a little argument to show that we can find some traps. So if we're not convex, there's some lambda, some potential lambda that we could use so that we took our limit set and our limit set translated by that guy. The two of them would be together be transverse. So what we want to do is find a pair, un and vn, pair of words in gn, such that if we take un of lambda and vn of lambda, and we rescale them so they look like copies of lambda scaled by z to the n. So let's rescale them by z to the minus n. Having rescaled them by z to the minus n, one is translated from the other approximately lambda. That's what we'd like to do. If we could do that, then the configuration of u of lambda and v of lambda would very closely resemble the configuration of lambda and lambda plus little lambda, poor choice of word, and that would prove we had a trap. So we just need to show that there is a u to the n and v to the n with this property. But notice what we're doing here. We've multiplied by w to the minus n, and w minus n is a big number. So un and vn, the difference between them is going to be very small. So we need to find points un and vn, the difference between them is small. Well, if we're in the Mandelbrot set Z, then we have infinite words, u infinity and v of infinity, whose difference is 0. So at Z, the difference is 0. So the difference between them is a function of Z. It's a holomorphic function. It's non-constant. It takes 0 at the value Z. There's a neighborhood of Z that maps onto a neighborhood of 0. You can approximate the infinite words u infinity and v infinity by finite words un and vn. The difference between un and vn hits a neighborhood of 0. When you rescale by z to the minus n, hits an arbitrarily big neighborhood of 0, in particular, big enough to find this nice translation vector, which is promised you by the fact that this thing's a non-convex set. So that's the end of the proof. Okay, so that's kind of nice, and then you can use these interior sets. Once you've kind of have a nice sort of technique for finding them, you can find them systematically. You can use this to give new proof of the existence of holes. And then you can show that these traps, they persist, they behave in a nice way under certain operators, these so-called renormalization operators, which are sort of at the heart of these self-similarities that Solomiac proved, that they had the similarities at these landmark points. You can prove that these traps persist nicely under renormalization. So once you've found a suitable loop of traps circling a kind of limit point, you can prove that this loop of traps persists when you shrink it down, sequence of loops of traps which kind of center down, nest down concentrically around this limit point, and you can prove that there's infinitely many holes. All right, so I'm going to stop at that point.